So I know everybody hates it, so we're going to do it again anyway. We could look at the process of making sandwiches. This time we've got 3 ingredients, so it gets a little bit more complicated. So we've got our bread, we have cheese, and we've got meatballs. Meatball sandwich, doesn't that work? Is it 3 ingredients? I needed something with 3 ingredients. And so it's talking about how you would go through and assemble that. And if we look, you might go through and say, well, you got 2 slices of bread, right? Depending on the size of the sandwich, you're probably looking at 3 slices of cheese. And meatballs, you probably got like 6 meatballs. So you've got a whole bunch of different numbers that go into this when we're trying to make that sandwich. If you were making it in and of yourself, it's probably not a big deal. You just take whatever ingredients you've got. But if we spun this around and said from a sandwich shop's perspective, what do they have to do to prepare? They're trying to think through how many people are going to order a meatball sandwich, okay? And if they're going to order that, how many different slices of bread do I need? How many different slices of cheese? How many different slices of meatballs? So that they're prepared to be able to make that, okay? And that becomes kind of the issue when we deal with these kind of conversions, is that we're used to individual scale. We're not used to macro scale. Right? And we're doing chemistry. It sounds a little bit weird, but we're talking about it at a macro scale, which sounds really counterintuitive because these are really, really tiny reactions that are happening. But the amount of reactions that are happening, the number of reactions that are happening is through the roof. Okay? And so that becomes kind of this weird dichotomy between them. So if we go through and look at our question, sorry, I'm trying to process all the pieces we got in here. We'll call sandwich. How many moles of sodium hydrogen carbonate? Okay, so that would be our sandwich. How many sandwiches can we make? When we have 1 mole of sodium carbonate would be our bread. Water is our cheese, and then carbon dioxide is our meatballs. Okay? And as we go through and think about this, when we're building that sandwich, we're looking at each of those, the bread, the cheese, the meatballs, all independent of each other. We don't add them all up to get the sandwich necessarily. We say, well, when I have that loaf of bread, I'm going to make 16 slices of bread. Well, how many sandwiches can that turn into? So what you're looking at is a kind of a larger scale within that system. So to start off, we have to realize that we're going to run this calculation 3 different times, which hopefully I'll be able to cram in onto this slide. Well, what are we aiming for? What's the end goal for our calculation? Well, it's the moles of sodium hydrogen carbonate, which is a massively long name. And so we could abbreviate it by going through and using the formula, NaHCO3. We could also abbreviate it by just making up any symbol that we wanted to. That is perfectly acceptable to go through and solve this. So what do you guys want? Sodium hydrogen carbonate, or do you want a new symbol?
Just do a square.
Do a what?
A square. A square.
Wow. Okay. Square. I didn't even cross my mind to use shapes, but that works. Okay. If we're going to start to bring in different symbols, we do need to acknowledge what that shape is, so putting it up in our equation could be useful as well. Okay, I'm going to start with my bread. How do I convert the bread across? Okay, so when we look at the bread, I've got 1 mole of sodium carbonate. So if we're going to set up our conversion, we need to bring in that mole of sodium carbonate. Where should I place that unit? On top or on bottom? Okay. Heard mole, sodium, it was just sodium carbonate, right? 2CO3. Okay. Perfectly acceptable. You're confident at the bottom? Let's put it on the bottom. Okay. What's the number that goes with that? NaHCO3 is not a number. 1. Straight from our given information. What should show up on top? Okay. So there's an interesting statement. For those people that went through and said, I want to put sodium hydrogen carbonate on the bottom, okay, they're now saying they want to put something else on top. Okay. This piece of given information because this is what I asked. That piece right there, where should we place it? That given piece of information has nothing else associated with it. Which means when you were saying to put it on the bottom, what are you saying you're putting on top? Nothing. Okay? And this does become some of the confusion because we will see these units appear in a variety of different locations. They have to. That's how we can cancel units. But the number that gets tied to them comes from where we're getting that information from. Okay? Since I started with asking about that mole of sodium hydrogen carbonate, our blue box, we're going to stick with that, which means the number that should appear on top should be 1 because it's not related to anything else. Okay? And Jiva, I perfectly accept. You can be unhappy with this, and you should be unhappy with this. Okay? Because now what do we need to do? We need to cancel that unit, right? So I would need moles of sodium carbonate. If we're drawing this, I would recommend not drawing this. Okay? And we'll see why in a second. That unit has to, and thankfully the technology is not working with me. It's not writing. Yeah, it's not writing at all, which will be frustrating, but we'll see if we can't bring it back in a second. Oh, there it went. Not only do I want to cancel that unit, what else do I want? So you have to be lockstep. What's your goal? All the way through. What's the goal of this calculation? Moles of sodium hydrogen carbonate. So yeah, I can set up this calculation where I can get rid of the moles of sodium carbonate, but what do I want to relate the moles of sodium carbonate to? Ideally, I relate it to the sodium hydrogen carbonate. Okay? And that should set up a problem. Why does that set up a problem for me? Where am I now placing my powerful unit that I want for my answer? In the denominator. Where did I want it? In the numerator. What does that mean about my initial step?
It's wrong.
My initial step in this whole process was wrong. Okay? I want you to realize that you can make mistakes. That's okay. You just have to acknowledge that you've made a mistake and then backtrack out of it. Okay? In the case up here, it's really easy because how do I backtrack out of it? I just erase it all and I rewrite it. And it's relatively easy for me to go through and erase. Okay? On your paper, how would you deal with that? You could bust out an eraser or you just put a line through it and you start your calculation again. Okay? So I want to go back to that initial question. We've got that blue box. That's our given piece of information. I want to use that given information. And again, the question I'm going to ask is where should I place it? Should I place it in the numerator or the denominator? Okay? Why should we place it in the numerator?
Because it's given, so it's associated with just one.
I was also given water. I could be given tons of different things. So just because it's given becomes a very questionable action to take. Not wrong, questionable.
So there's 1 mole of sodium carbonate in the balanced equation.
That's bringing another piece of information. So why should I place it in the numerator? We do have a pretty easy out. What happened when we put it in the denominator? It was wrong. So why should I place it in the numerator? Because I know the denominator is wrong, and there's only 2 places, so it's got to be in the numerator. That's not a horrible method. That's a little bit slow. Okay? So we like a little bit of a faster process. Okay? What do we want for an answer? Moles, stop. Blue box. What's my measurement unit? Moles. Where do I want my moles to show up in my answer? In the numerator. So where should my moles show up in my calculation? In the numerator. So I can let the unit help tell me where to make that placement. Okay? Is that what you've got written in your notes for those people writing? Yeah? Or did you instead write 1 in front? What did you write? I don't know where you got the 2 from, because that says fucking 1.
Yeah, but you wrote sodium hydrogen carbonate, not sodium carbonate.
So I'm the asshole. You're right. So let's fix that.
Why couldn't you?
Because what we were doing was manipulating what we had, our given information. Okay, so that should be moles of sodium carbonate. When should we write the number 1? Okay, when it was given. So yes, it was given. Did I write the 1 first? No, what did I write first? Write the unit first. The unit is going to dictate your placement of the numbers. So if your unit is present and correct, your numbers will then necessarily follow correct and proper. Does that make sense? What should show up in the denominator? 1, because it's not related to anything else within that blue box. Okay? Is that equality true? Is moles of sodium carbonate the same thing as moles of sodium hydrogen carbonate? Nope. So what do we have to do? You have to do some kind of conversion. The question becomes is what conversion do you want to do?
Similar ratio, right?
Okay? And varying answers could come through with this. You could jump to, oh, I've done this a whole bunch, so I know the answer is blah. Or we could be like, I don't know what's supposed to show up there. And I would argue the vast majority of people going through and trying to solve chemistry do not know what belongs there. They haven't done enough practice to find it. Right? Which means, what's your process if you don't know what belongs there? And silence is most often the response. The whole point of this is to track your units. What has to happen to the moles of sodium carbonate in blue? That has to cancel. The only way it can cancel is if it appears in the denominator. What do I want to appear in the numerator? The moles of sodium hydrogen carbonate. Okay? What I'm trying to establish is the conversion factor that I want. Okay? That's where we start. That's what I want to have. And now the content of this unit is going to come in and hit us. Because what we just did right there isn't this unit. That's unit 2. And you're like, well, this is new to me. It's not new to you. That's exactly how I taught you to do it in unit 2. And the next question that now brings in unit 3 is, does that conversion factor exist? That's the part you're supposed to have spent the last 3 weeks preparing for. Well, does it exist? That does exist. I'm converting one substance to another, and the only place to convert substances is found in the balanced chemical equation. So I would go back to my chemical equation and ask, is it actually balanced? Okay. That would be unit 2 stuff. You track through it, verify, yep, that one's a balanced chemical equation. Okay, now that it's balanced, I can pull the coefficients from that balanced chemical equation. How many moles of sodium hydrogen carbonate does my balanced chemical equation tell me? 2. How many moles of sodium carbonate does my balanced chemical equation tell me? 1. What happens with my units? The moles of sodium carbonate cancel. What units would I have now? What units would I have now? Moles of sodium hydrogen carbonate. What did I want for an answer? Moles of sodium hydrogen carbonate, which means I'm done. Now I just do the math. 2 divided by 1. 2. 2 times 1. 2. Which means if I just look at the moles of sodium hydrogen carbonate, just my slices of bread, I can get 2 moles of sodium hydrogen carbonate. That's what it tells me. Okay. Do I have more information, though? Is there other stuff that I have to worry about? Yeah. I've got the cheese and the meatballs to worry about. So what do? We can move to the next one. Let's take a look at the water. Okay. And a couple people suggested a different path through this solve. So let's go through and poke at that different path. Okay. Moles of squares. So we can go through and say, well, moles of squares, and I'm trying to tie this back to the water somehow. Okay. And we do have to realize that this 1 and this, come on, color work with me. The 1 and the mole tie back to the water as well. That's our English language biting us. Right? We can look at it, well, I have 1 mole of water and I have moles of squares. Those are not the same substance. So right away I can say, I'm going to do a substance conversion. Where do I find a substance conversion? Balanced chemical equation. Okay? So I'm going to start to pull the information out of my balanced chemical equation. Okay? In that information, what unit do I want to appear in my numerator? Moles of squares. What unit do I want to place into the denominator? 1 is not a unit. 1 is a number. Just like I'm a sixth, it has very little meaning until you associate a unit with it. What unit do I want to appear in the denominator? In the denominator. I want squares in the denominator. What would happen to my units of squares? They'd be gone. I don't want to get rid of them. Moles of squares is fantastic. What am I starting with? We've shifted our focus to the water. So I need to relate the moles of squares to the moles of water. Okay? That's how I can convert my substance. Where do I find the numbers associated with that conversion? I go back to the chemical equation. I put the squares in the wrong spot, didn't I? Two moles of squares was equal to 1 mole of water. Do I have my answer? No. What has to happen? I need the moles of water to cancel out, which means moles of water better appear in the numerator. Do I know anything about just the raw moles of water? Yeah, the question tells me I have 1 mole of water. What's in the denominator? 1, because it's just 1 mole of water. That's it. What happens to my units? The moles of water cancel, and I now have moles of squares. Is that what I wanted? Yeah. Now I can run the calculation, and I get 2 moles of squares. Okay. That was looking at our bread. We looked at our cheese. Now what do we got to do? Meatballs. Okay. I got to figure out what's going on with the carbon dioxide. Where do I want to start this conversion? Do I want to start it with the carbon dioxide? Do I want to start with the conversion factor? Start with the carbon dioxide. Where do you want to place it? Why do you want to place it in the numerator? You are 100% correct. Look at the unit that we have. We have moles, that's my measurement, and the substance. We look at my answer. I've got moles in the numerator. I'm going to keep the moles in the numerator because that's exactly the placement of that unit that I want. Okay? From the question, I'm given 1 mole of CO2. That's 1 mole of CO2 chilling on its own, which means underneath, it's just a 1. Are those two equal to each other? No. So what has to happen? I need to run a conversion. In that conversion, I want the moles of CO2 to cancel. Actually, I'm going to delete that. want to lean into your statement. Okay? Because there's multiple ways. We went through painful way 1. We went through painful way 2. We don't know what these things should be. Okay? Except somebody said, well, I know I need to use a mole ratio. Okay. You need to do a mole ratio. In that mole ratio, you know that you need moles of CO2 and you need moles of, we're at squares, right? Squares. Here's my mole ratio. That's a mole ratio. What's wrong with it?
The wrong way.
It's the wrong way around. So what we're trying to do is pay attention. It's not just do I need a mole ratio. It's how does that mole ratio get used that has to be tracked. My moles of CO2 needs to appear in the denominator so that unit can cancel. My moles of squares needs to appear in the numerator. What are all my numbers? 2 and 1. And we go through and we get 2. Okay. Again, what happens? Our units cancel, and we've now gone through and said that if I start with 1 mole of sodium carbonate, 1 mole of water, and 1 mole of carbon dioxide, I get a whopping 2 moles of sodium hydrogen carbonate. Did I get 2 or 6? So you asked me 2 plus 2 plus 2 is 6. So what's the answer? Okay. Just like with our sandwiches. If we go through and find out the bread can make 14 sandwiches, the cheese can make 2 sandwiches, and the meatballs can make 1, how many sandwiches do I get? I don't add all those numbers up. I only get 1 sandwich. Because what happens? I ran out of frickin' meatballs. It doesn't matter that I have extra bread. I can't put any more meatballs in the sandwich. The same thing is going to happen here. This one gets a little bit trickier because the numbers are all the same. Okay? But I'm limited to 2. I can't make any more than 2. As soon as I've made that 2, what happened to my moles of CO2? It's gone. I can't make any more. There's no more CO2 to be able to make more sandwiches. Kind of, sort of? Harder question. What's the limiting reagent? So the limiting reagent is the reagent that limited how much sandwiches, how much product I could go through and make. Okay. We get the exact same amount for all of these, which means they're all the limiting reagent or none of them are. Both are perfectly acceptable answers. Does that help you to understand that question? Eden, do you still have a question?
No. I
No?
was just gonna ask if we could do a problem on like converting molecules or like
Okay.
the liters over or molarity.
Yes. Are we good with this question? Okay. Pause while as we go through. So what we're going to do is start with, I have a solution of silver nitrate. To know it was a solution, what do I need to see? I need to see those phases being aqueous. So I'm going to take 2 solutions. I mix these 2 solutions. We'll reveal more information about them as we go. Okay? When I mix these 2 solutions, do I see a chemical reaction? So this is review content. Believe it or not, the final's creeping up real fast. Yeah. Okay? How do I know I see a chemical reaction? What type of words? What type of chemical reaction would this potentially be? This should be a double replacement, so we'd go through and we'd swap out our species. We'd get the Ag with the Cl. Should this 2 move?
No.
Why not?
It's associated with copper, not.
Okay. The meaning of that 2. So if we go back to that 2 in the starting material, why is there a 2 there? It's to balance out the copper. There's 2 chlorides to balance the copper. The 2 is not part of the identity of the chloride. It's part of the balancing of it. Since the chloride is no longer with the copper, we don't bring the 2 across. Okay, will it become important? Yes, we'll worry about that later. All right, what else do I produce as a product? Cu with the NO3. Okay? Before we get into predicting whether there was a chemical reaction, did we predict the products correctly? We did not. Copper on the reactant side was bonded to 2 chlorides. What's the charge on chloride?
-1.
Chloride's a -1. If chloride's a -1, what was the charge on the copper? A +2. Which means when I go over to the product sides for my double replacement reaction, we assume it stays constant, which is a bit dodgy outside of this classroom, but it's fine inside this classroom, which means that copper is still a +2. What's the charge on nitrate? A -1, which means those charges don't neutralize. I need 2 nitrates. If we go back to that chloride for a second, we said the 2 doesn't move across, right? But the 3 for the nitrate did. Why? That 3 is part of the identity of the nitrate. That's why it stays with it. All right? Is this balanced? No, so we'd have to go through and do the balancing. How are we going to balance it? Okay, so you can go through and do one element at a time. Okay, ideally, as you go through that one element at a time, you're going to find out that we need 2 silver nitrates and we'll need 2 silver chlorides. Okay, you should prove that to yourself. Make sure you've got that. Now, how do we decide that we had a chemical reaction? When we're looking at double...
On the products, the solubility rules.
Oh, okay. Sorry, I thought you were saying I did something wrong. I was like, it's been that day. Okay, so to decide double replacements, this is exactly right. We have to look at solubility rules. Okay, you're not required to memorize them. You are required to look them up. So if this was on a test, you'd flip to the front of the exam and you'd see your solubility rules. One of your solubility rules would say chlorides are, actually, I think they're always soluble with certain exceptions. Lead and silver. I don't know. I'm hoping I'm right. I know silver is. Lead and silver are an exception to chloride being soluble. If they're an exception, what does that mean? It's insoluble, which means phase is a solid. Okay? The copper nitrate, we already defined one, so we're probably okay just dropping that in as aqueous. Anything with a nitrate is water soluble. I do know that one. Okay, so that one would be aqueous. So we do have a chemical reaction here. All right? So we mixed these 2 liquids and we produced what's a good number? Let's pick 3.14. That's a good number. 3.14 grams of silver chloride. All right? If we think through the context of this question, some more information was involved. One of those pieces of information is we needed to know some information with a molarity in this. Right? So for the solutions, this is starting to get tricky. I think I can pull it off. We started with a 2.00 molar solution of silver nitrate. I got to run some calculations in my head. I think we're going to stick with that and hope for the best. Yeah, I may regret that decision, but we're going to try it. how many molecules of silver nitrate reacted? Be grumpy. I think we can do it without actually doing what I wanted to. Yeah. We'll add another question. What was the volume of the silver nitrate solution? I was hoping to get away with it in one question, and I don't think I can do it in one question. At least not off the top of my head. So we got two questions. How many molecules of silver nitrate reacted? And what was the volume of the silver nitrate solution? Those are the two things that you are now responsible for working through. Should we start working through it together, or do you guys want to just try first? Couple people said they wanted to try first. Couple people said you wanted to work together. So we're going to try first for a little bit. I'm going to rewrite those questions into straight lines so I can get a little bit more space to write stuff out for a calculation. But then I'll slowly start working into that solve. So start working it, put together what you can. So capital M is molarity. What does molarity mean? Moles per liter. So anytime you see capital M, what should you immediately do? You should rewrite that as moles per liter. Okay, the number in front of liters needs to be 1 so that it doesn't change the 2 above it. Okay, the substance for your moles is silver nitrate because it was coming from that system. So this is an interesting one with 2 questions here and 2 pieces of given information. How would you decide what to start with? Okay. If you don't know, that's quite all right. Just start trying to slug away at it and see what happens. What you will end up discovering is only one of those pieces of information is useful for one of those questions, and probably the question you're starting with. So you've got to decide which thing to start with, and your question would be, why are you starting with that one thing? Okay. So for that first question, I want to know the molecules of silver nitrate that reacted. For the record, dumb question, we'd never ask this. Right? If we look at the scale of the reaction, we're looking at 3 grams, 2 molar solutions. It makes no sense to look at the number of molecules or even atoms that reacted. It's a silly kind of conversion process to go through and do. So all we're testing is, do you know how to use it? That's it. Okay, so where we prefaced initially was, which thing should we start with? Should we start with the 2 moles of silver nitrate per liter or the 3.14 grams of silver chloride? And I would argue that's a tough question to go through and do. Okay? We might stick with the 2 moles per liter because that at least has the same substance. What we'll end up finding as we go through to navigate that is that we're not going to have a way to get rid of the liters. That unit isn't going to disappear. Okay? So which means we need to be using the 3.14 grams of silver chloride, which does get problematic because the way we're choosing it, or the way we've described choosing it, is because we attempted one and it failed, then we moved to the other one. That's a bad method. Okay? So we'd like a cleaner method. The best method, or the cleanest method I've got, is not a happy one in my opinion, but it is something that mathematicians have told me all the time. If we look at the units, our 2 moles per liter is a complex unit that has 2 pieces of information tied within it. If we look at what we're trying to solve for, we're trying to solve for a single unit. Okay? So the thing that we should be starting with is the thing that has a single unit tied to it. Kind of, sort of? Okay? And if you don't like that, that is okay. You should go through and prove that you hit a dead end pretty fast. Okay? So we could now start to set this up. If we're going to be starting with our 3.14 grams of silver chloride, we're going to have an interesting dilemma here. Grams is not molecules, and silver chloride is not silver nitrate. So we know we're going to have to do several conversions. Okay? Right? Since we know we have to do several conversions, what should we start with? If we start with that 3.14, where do we want to place it? Should it go in the numerator or the denominator? And if you can't answer that question, that's okay. But what that means is you have to step back and say, I need to deal with some other way to convert. Okay? Go back to some other truth. Is there a conversion factor that relates grams and molecules? Is there? You should look at that a little bit more carefully. There's not a conversion factor that relates grams and molecules. Grams is macro, molecules is micro. Okay? Those are opposite systems. We don't have a system to relate those two. That's actually two conversion factors at a minimum. Okay? Is there a conversion factor that relates grams of silver chloride versus silver nitrate? Is there a conversion factor that allows me to convert one substance to another substance? Okay? That's the one that everybody should be, yes, absolutely. And why should you be saying yes, absolutely, to how you convert one substance to another substance? Because the name of this class is chemistry, and that is arguably the only chemistry thing we talk about, is how you convert one substance to another. Everything else we're doing is just conversion, quantification of stuff that's already addressed in tons of other classes. The only thing that is unique to chemistry is how we're turning one substance into another substance. That goes all the way back to Philosopher's Stone. Like, that's literally what we do. That's chemistry. So when I ask, is there a conversion factor between substance and substance, that should be, yes, of course there is, Mike. It's obviously in the balanced chemical equation because that's the only thing that's unique and new and interesting in this class. The rest of it is just nonsense. Yay, chemistry. You don't have to echo, I guess. Like, the recording caught it. It totally heard that feedback. That was cool. Okay, so I would argue for me personally, I'm going to start with that chemical expression. Okay? And that chemical expression, I know that I want moles or the molecules of silver nitrate to appear. So I want silver nitrate to appear in the numerator because that's where it is in my answer, which then means the silver chloride needs to appear in the denominator. I'm trying to convert a substance here. The only place I can convert the substance is the balanced chemical equation. What unit is tied to the balanced chemical equation? Moles. So I can now bring in that measurement unit. This comes from my balanced chemical equation, and this one's a bit dumb. Admittedly, I chose the wrong things to convert, and that's okay. This is 2 and 2. Those are the coefficients straight from our balanced equation. We now have a foothold in our question, so now we can attempt to go through and solve. Do I want moles of silver nitrate in my answer? No, so I'm going to need to get rid of that. Do I want moles of silver chloride in my answer? No, so I'm going to need to get rid of that. Okay? If I tried to go through and do that in a single fell swoop, what's going to end up happening is I would just copy the conversion factor I already put there, which means I'm just going to have to pick one that I want to manipulate. Which one do you want to manipulate? Silver nitrate or silver chloride? Nitrate. What has to happen to the moles of silver nitrate? It needs to be canceled. Okay, so I have to place that in the denominator. Okay. What do I want to place in the numerator? Why do you want to place molecules? Because grams is a perfectly valid conversion as well. Why do you not want grams? Look to where our answer is going. We want molecules of silver nitrate. So if this conversion factor exists, this is going to still solve two things. I get the answer I want, the unit I want, and I get rid of a unit that I didn't want. Is this a conversion factor that exists? Yes. Where does this exist? Now I've just bollocksed it all up. A number. Let's just stick with that. Okay? An A number tells us 6.022 times 10 to the 23rd molecules is 1 mole. If we track our units, the moles of silver nitrate would be canceled, and I would get molecules of silver nitrate. Hell yeah, I want that. But I don't want moles of silver chloride. So what does that mean I have to do? That has to cancel out. So I need moles of silver chloride to appear in the numerator. Do I know the moles of silver chloride? Where does it tell me the moles of silver chloride? Balanced chemical equation. Did I already use the balanced chemical equation? Yes. So if I go back to the balanced chemical equation, all I'm going to do is undo the work that I've already done. So I want to find a different conversion factor. What could I relate the moles of silver chloride to? Why do I want to convert it to grams of silver chloride? That was that given piece of information. I know a little bit about the grams of silver chloride. Right? So if this conversion factor exists, this is going to allow me to cancel units. Does it exist? Where does it exist? This comes from the periodic table. This is the relationship between our mass and moles. Anybody actually get a number?
143.32.
Grams is equal to 1 mole. The number coming off the table is the mass value. Okay, so what happens? Grams of silver chloride, whoops, not that one. Moles of silver chloride cancel, long distance. Great, I didn't want that unit, but now I've introduced grams of silver chloride. Did I want that? So what has to happen? I need it to cancel. Do I know the grams of silver chloride? Yeah, that was actually my given information. That was 3.14 grams of silver chloride. Given information, the grams of silver chloride cancel. What happens? Where are we at now? Now we can solve. The only unit left over is our molecules of silver nitrate. That's exactly what we wanted. We can now do all the calculations and punch into the calculator. Okay? Everything is set up. Everything is in place. Note, as we go through and do this, what are we putting underneath each of those pieces of information? Arguably, I screwed this one up. Where did I get that first piece of information? First piece of information on the left. This was our given piece of information. So as you go through and solve, you should be pointing out where that information came from. Okay? That's going to help you understand how to solve in the future. How do I find those relationships? Where are they coming from so that I can navigate those systems later on? That's the point. Expert tip, if you've looked at the practice exam, you probably see a question that talks about doing this. It's probably a really big deal considering that every single time we've solved, what have we done? Point it out where every single conversion factor comes from. What do you think is going to show up on your exam next week? Yes, this is part of your required work. Tell me where that information is coming from. Okay? This sets us up with the molecules of silver nitrate, so it gets us the molecules, which is fantastic. Okay? However, it didn't bring in the molarity because we don't have any moles per liter, which is why we've got that other question. What was the volume of silver nitrate added? Okay. To answer that question, we've got a variety of different tactics we can take. We've done a whole bunch of work, so we could use that work and leverage that, but I think that's cheating. So instead, what we're going to do is take a hot second for me to ask, do you have written down everything you want written down? Okay. If you have not, you can take notes on 4420. That is the time in the video you need to navigate back to. What are we being asked for now? Yeah, fair. It just says what's the volume of silver nitrate added, which means we can pick any volume unit we want. The unit that makes the most sense would be Liters because the unit of molarity is in liters. Okay? And officially, this isn't liters of silver nitrate. It's liters of solution of silver nitrate. Okay? Which sometimes becomes a problem, but typically not. You're usually okay to just acknowledge it as silver nitrate. So, what do you want to start with? The given information. There's 2 pieces of given information. I need more. Okay. You want to use the molarity? Okay. So we'll use that given information where it was liters of our silver nitrate per mole of our silver nitrate. We had 1 liter was 2 moles, yeah? Okay. We're placing the 2 in the denominator because we want liters of silver nitrate to appear in our numerator because that's where it appears in our answer. Cool, we have a place to start. Do you want to try and leverage what you've got, see what you can come up with on your own, or should we solve through it together? Together, okay. There's some confidence, come on. What do you know has to happen? We need to get rid of, come on, pen, moles of the silver nitrate, because I don't want that. Okay. What can I relate the moles of silver nitrate to? I could relate it to the moles of silver chloride. I could relate it to grams of silver nitrate. I could relate it to molecules of silver nitrate. All this is about is trying to recognize your given information. How can you pair through? What other things can you potentially bring in? What do you got, Eden?
Isn't, I thought you would do 1 mole is equal to 22.4 liters.
We'll come back to that one.
Okay.
But no.
No?
Nope, we're not going to do that one.
The grams of silver chloride.
Okay. We have grams of silver chloride. Okay. I know that's how much was produced. Can I relate my silver nitrate to the grams of silver chloride? How would I relate the moles of silver nitrate into the grams of silver chloride? Does that conversion factor exist? Okay. And if you're saying yes, that's okay. Where does it exist? Periodic table. Okay. How many moles of silver nitrate per gram of silver chloride is on the periodic table? There's the problem. The periodic table does not relate substances. It relates a single substance, the mass to the moles. We have 2 substances here, which means, does this conversion factor exist? No. It is perfectly acceptable to write it and acknowledge that that's what you want, but just because you want it doesn't mean you get it. Okay, so what do you want to deal with? The grams of silver chloride or the moles of silver nitrate? Moles of silver nitrate? Okay. What do you want to relate the moles of silver nitrate into? If we relate those into moles of silver chloride, we can then potentially launch into a different calculation. Okay, and we can look at that in a second. The other option that we'll leverage here, why not go grams of silver nitrate? Can I do that? Yeah, I absolutely can. Okay, do not take notes. Okay, the moles of silver nitrate would cancel. I'd get grams of silver nitrate. What do I want to relate the grams of silver nitrate to? Well, again, ideally, grams of silver chloride. Because I know that number. Is there a conversion factor that relates those 2 things? No, there isn't. Okay? I don't have a mass of one substance related to a mass of another substance. What I'm trying to do is convert substances. What unit must I be in to convert substances? Where do I find the conversion factor that relates substances? Balanced chemical equation. And the unit from the balanced chemical equation is moles. Which means going into grams of silver nitrate doesn't help us. What it's ultimately going to do is take us down a path that prevents us from solving. So what we actually want to do right out of the gate is convert the moles of silver nitrate into the moles of silver chloride. That conversion factor is found on the periodic table, 2 and 2. This was our balanced chemical equation. This one was given. It was a given. Concentration is the name of that. The moles of silver nitrate would cancel. I need to get rid of the moles of silver chloride. How do I get rid of the moles of silver chloride? Do I know anything about the moles of silver chloride? I'm not given a numerical value for it, but could I relate the moles of silver chloride to something else? How about to the grams of silver chloride? Do I know a conversion factor that relates those two pieces of information? Yeah, where is that information found? That's on the periodic table. Right? I want to highlight something here. By writing grams of silver chloride, it is very common that we will find students doing this, 3.14. Why did they do that? You have given information tying that number to that measurement. That's true. Is it tied to that conversion factor? No. This is why you have to write the units first to identify the conversion factor before you start dropping in numbers. You told me it already, 100 and something?
143.32.
143.32 grams, 1 mole. We're assuming that was done correctly. I trust the source, but you don't have to. Okay. What happens? The moles of silver chloride cancel. What do I need to do? I need to get rid of the grams of silver chloride. Do I know anything about the grams of silver chloride? Yeah, the question actually explicitly told me I had 3.14 grams of silver chloride. What's in the denominator? 1, because it's not related to anything else. Now what can I go through and do? I can punch it into a calculator and I would get my liters of solution. Okay. In this particular case, was liters of solution a good measurement unit? Everybody's like, well, how would you know that? We'll find out here in a second when Logan tells me the answer. No pressure. I'll pause so no one knows. Okay. We'll assume the calculation was done correctly. We get 0.0109 liters. We'll ignore sig figs, though I conveniently wrote down the proper sig figs. That's fun. All right. Is that a good measurement unit for liters? It's kind of a weird question. I would argue no, that's not a good unit. Okay. Do you like measuring fractions? No, what do you like measuring? Whole numbers. That's not a whole number, so what could we do? I heard someone talking about powers of 10. I think that's sort of the right idea, but powers of 10 are just going to make it more complicated. What we could do is convert this into milliliters, and we'd be looking at 10.9 milliliters. Is 10.9 an easier thing to measure? Yeah, I think I did that conversion right. Okay.
So the answer's still be correct if you did
This question was poorly written. This question was poorly written. You could use any unit you wanted, and if you wanted to use powers of 10 and do 1.09 times 10 to the negative second, that's fine too. 1.0? Yeah. That would be perfectly acceptable. Everybody kind of track? Hi. There was another very useful question that popped up. Trying to think through how I can get it in. I can't get it in cleanly. So I'm going to erase everything again. We good with that? Okay. Here's the eraser we're going to go through and do. And I want to draw your attention to a couple different things. Okay. First and foremost, we had a conversion factor 2.00 moles. I'm going to ignore the substance per liter, right? Okay. There was another suggestion for a conversion factor. 22.4 liters equal to 1 mole. Okay. do these conversion factors relate the same things? A little bit of a gray area. Right? Well, one is moles to liters, the other one is liters to moles. Aren't those the same thing? Couldn't we just flip those around and come to a different number? Yeah, I mean, technically, yes. But they're very specific about what they're referencing. When we look at the one in blue, that 2.00 moles per 1 liter is 1 liter of solution. Okay, so what this is talking about, if we looked at our chemical equation, that's supposed to be an arrow. It's not getting any better. Oh, it got a little better. Okay, was AgNO3, and how do we know it was a solution? It said aqueous. Where's the 22.4 liters being related to moles coming from? This is, man, I'm not getting any better with those. Okay, this is very specifically referring to a gas. Okay? So the concentration for a solution is defined as concentration, and in chemistry we use the term molarity. But you've seen concentrations in other places before. Okay? Of course, the concentration examples I've got are not age appropriate, I guess, necessarily. So we'll pretend those ones didn't happen, but we could look at Kool-Aid. There's a little more age appropriate. Right? If you take Kool-Aid, right, you could just take the powder and you could just eat the powder, right? Oh, that's disgusting. That's Fun Dip, right? It's the same thing. Right? Or you could pour it into a small cup of water, or you could pour it into a really big pitcher of water. That's changing the concentration. Okay? How much of that substance was dissolved into that solution? Okay? The other one for a gas is how much that gas particle, what volume does it occupy? So it's a similar system, except in the solution, there's a solvent. There's another material floating around in between those individual target molecules. In the case of the gas, what's floating around in between the gas molecules? I love it when I ask a question and the answer is appropriate. Nothing. Nothing is between them. It's a vacuum-ish. Okay? There is nothing in between those gas particles. For the gas, this is pure. This is a mixture. Which is why the numbers will change. For the gas, that's sort of semi-constant. Okay? For the mixture, that's going to depend how much I dissolve into it. But for a gas, for a given pressure, volume, temperature, moles, I can change the moles and they're still going to occupy the same volume. That's a constant relationship. Okay? So as long as I'm at a gas, I know 22.4 liters is 1 mole, and that's a lovely conversion. But if I'm not a gas, I can't use that conversion factor, and I must use concentration. Okay? And that is a really hard thing to differentiate because the units that we're comparing look very, very, very similar. Pay attention to the substance. If it's a solution, concentration and molarity. If it's a gas, have at it with your 22.4 liters is equal to 1 mole. Because you all watched the video, I don't need to complain about that, right? Or should I complain about that too?
You complained about the video.
Somebody clearly watched the video. Okay? If you haven't watched the video, it might be entertaining. You could also like triple speed it there and just click ahead. How far did you have to click ahead?
I waited.
Okay. Okay? Because the gas one is very particular. It's only true at standard temperature and pressure, and I'll leave it at that. I'll try. We're never at standard temperature and pressure. This is a freaking stupid conversion. Should never make you do it. Okay, different question. Fast, please. You got nothing?
Is there an easier way to do percent yield than having to go through all of them?
So, yes.
Because I feel like the process is so long.
Okay. So let's lean into that a little bit. Okay. The process is so long, Mike. This is awful. Why would you make me go through and do this? No. How do you calculate a percent yield? That's how you calculate it. Okay? And that, believe it or not, is really it. And we'll see where the it comes in a second. Right? So what we could go through and do is we have to know what the actual and theoretical is. Because 100, that's just the number, 100. Easy, right? Right? In this particular system, what we would go through and do is call this number here our actual. 3.14 grams of silver chloride was actually obtained. Okay? We don't typically say actually attained because that kind of is a big tip. Okay? So instead we would just say were obtained. If we're going to ask you a percent yield question, typically what happens is we'd go through and say we started with 5.00 grams of silver nitrate and determined we should have paused the video so this looks cooler. Should have made, looks like the mass will go down a little bit, so we'll call it 4.00 grams of silver chloride. What's the percent yield? What was the actual? 3.14. So I spit all over my stuff. This is my stuff. 3.14 grams of silver chloride. What's the theoretical? 4.0 grams of our silver chloride. Multiply by 100. And done. More or less 75% yield. You're like, but Mike, you made me do so much more work than that. I did. Why did I make you do more work? What was I trying to do? Give you practice for all the conversion factors on how you could tie those things together. That was all that reason was there for. When we look at how you calculate percent yields for the exam, this is it. Okay? Note, when we look at it, how many numbers were you given? You were given 3 different numbers. How many numbers did you need? 2. Why did we give you the 3rd number? We need some other kind of distractor number in there to mess with your head so that if you're just punching random numbers into the calculator, you can get a wrong answer. Okay? And when it comes to that, yes, 4 over 5 is a wrong answer. 3.14 divided by 4 is one of the wrong answer. 4? Nope. Divided by 5 is also in there as a wrong answer. 5 divided by 3.14 is also in there. Okay? And I believe even multiplying is in there as a potential wrong answer. Okay, so it isn't just a can I punch into the calculator, it's did you remember that your percent yield is actual over theoretical, and that's all the calculation comes down to. Okay, everything else that you saw within the videos is trying to give you that practice for how we calculate limiting reactions. How do we convert one substance into another substance? Because whether or not you agree, everybody needs more practice with those. Okay, but the actual percent yield stuff, really straightforward. Can we throw in a quick test on this? What if your number came out to be higher than 100? Does that mean you were wrong and you screwed up your calculation and you should do a different number?
No.
No, it doesn't. Okay, what does that mean?
That you made a mistake.
Whoever did the experiment screwed up the experiment. Don't screw up your calculations just because somebody else screwed up their experiment. Okay, it is always actual over theoretical. Can you get a number larger than 100%? Yeah, should you? No. Okay, that should comes back to the lab side. You're not doing any lab stuff here, so don't worry about that. Okay, focus on what the actual calculation is. Make sense? I got 2 minutes. Step on the soapbox and complain about STP while everybody left. If you don't have any other questions, we can end it there. I'm fine with that.